Hi everybody, welcome back to the Feynman Technique. So today we are going to step back from doing Gaussian type problems and we're going to circle back to a Frullani type integral. This one is however squared. This is exactly the standard Frullani integral, but the integrand is just squared. So let's see what we can get for this. All right, so first let's recall this formula that we derived very early on in this process. I believe it was one of the first formulas we derived using Feynman integration. So any integral of this form is going to evaluate to the natural log of our parameter b over our parameter a. All right, so now let's just define our target integral as a function of a, and we'll let b be some arbitrary constant. All right. And we'll notice that I of b is 0. If we let a equal b, the entire integral goes to 0. All right, now let's perform some Feynman integration here. We're going to take a derivative of our function of a with respect to a by moving the derivative inside the integral sign and taking a partial. All right, here are the steps to perform the partial derivative of that integrand with respect to a. We'll just keep going. And finally, um, we can represent the derivative of our function of a like this. And now we have it in this explicit form right here. You'll notice our b in this case would be negative 2a, and I'm sorry, our a in this case would be negative 2 little a, and our b um, would be a plus b. All right. So plugging those in, and we see that the derivative of our function is equal to negative 2 natural log of a plus b over 2a. So we can anti-differentiate that with respect to a to get back to our original function. And you'll notice that I split it up into two separate natural logs using the properties of logarithms. All right. So now we'll use this formula. The natural log of u is just u natural log u minus u. And we plug that in and we find that this integral is going to evaluate to this. And that this integral is going to evaluate to this. So combining them, and we have almost our final expression for our original integral I of a. All right, we just have this annoying constant of integration that we can solve for by using our initial condition that I of b is equal to 0. So if we plug in b, we know we get 0. That implies that our c has got to be this. So putting that back in, and now we have our final expression for our integral. Now this is messy and it can be simplified a lot. The first step is to simplify it like this, and then we use properties of logarithms and grouping to arrive at our final form. So any integral like this evaluates to this. And that's kind of neat. You'll notice there's some symmetry here. We have 2a over here and we have 2b over here. We're taking natural log of both of them, but inside we have 2a in the numerator over here and 2b in the numerator over here, with a plus b being in both denominators. I don't know. I think that's pretty cool. I hope you do too. I also hope you enjoyed that, and we'll see you next time.